This is Lecture 1, Week 1, Course Structure and Entropy. Lecture Notes in Information Theory. I am Hikmet Kamberay, a professor at Faculty of Engineering, International Balkan University. An outline of the course is shown in the following. First, I'll talk about the course administration, then I'll talk about entropy, some properties of entropy, joint entropy, and conditional entropy. First, we start with the lecturers of this course. I'll be the instructor of this course. My email address is hkamberay@ibu.edu.mk. The office will be a Rectorate building, second floor. The phone extension number it is 123. Use my email, please. Day of the week will be Monday, subject to negotiation. Hours it is from 10 a.m. Next, I'll talk about the materials and the aim of this course. The lecture notes can be found on the ELO system at elo.ibu.edu.mk. Course has to be registered at IBU. The lecture notes could also be found on YouTube as video clips with a subscription. You could also find it on the website hkamberaibu.wikidot.com with a registration via the website. Alternatively, via the email. Please provide me with your email address. The textbook of this course is titled An Introduction to Information Theory, which will be published on Lambert Academic Publishing during the academic year 2023-2024. Other literature includes Elements of the Information Theory by Cover and Thomas, which is published on Wiley and Sons on 2006. Published articles with particular interest will be given during the course for reading. The main objective of this course is to give an introduction to some elements of the information theory. From this course can benefit the students of computer science, communication theory, mathematics, nature sciences such as physics, biology, chemistry, engineering, economics, and statistics. The course material is primarily designed for senior and first-year graduate students. The learning outcomes of this course include gaining knowledge about the entropy and mutual information, gaining knowledge about information flow between time series, understanding the nature, algebraic structure of information theory, understanding the problems in data compression and communication. Next I will talk about the course structure. The attendance out of 10 weeks is at least 60% to take the exam, at least 30% for repeating students, no attendance for double repeating students. Credit points from semester course activity are 40 CPs for a semester project. That is 40% of your final CPs comes from the semester course activity, which is the project. The topic of the seminar work shall be chosen in the first 2 weeks of the lecture. The seminar work shall be delivered by the 10th week of the lecture, but it must be delivered before the exam. It shall consist from 7,500 up to 10,000 words. Tables, graphs are excluded. There are several exams for this course. First, the final exam, or make-up one exam, which is maximum 60 CPs. The credit points are calculated in this way. Total number of points earned multiplied by 0.6. Makeup 2 exam is also maximum 60 CPs. And there is an opportunity for the Makeup 2 exam in June, spring semester, the same academic year, without attending the classes. However, the course must be registered. Again, the credit points are evaluated as total number of points earned times 0.6. Upgrade exam, which is also maximum 60 CPs, it is also possible. There is an opportunity for upgrade exam with a period of 3 months from the final or Makeup 1 or 2 exams without attending the classes. However, the course must be again registered. Credit points are calculated as the following: total number of points earned times 0.6. Similar. Next, I'll talk about the grading system. The grading system that applies to this course, it is established by the university regulations. The credit points less than 50 are equivalent to a grade of 5. Between 50 and 60, excluding 60, is for a 6. Between 60 and 70, excluding 70, it is 7. Between 70 and 80, excluding 80, it is 8. Between 80 and 90, excluding 90, it is 9. And between 90 and 100, it is a 10. 5 is a failing grade. All the other grades are passing grades. The lecture format is as the following: for students with physical presence, 45 minutes lecture, 15 minutes break, which can be used for water, dinner, questions, and other things. Then follows with 45 minutes lecture and 15 minutes break for the same reason: water, dinner, questions, and others. Then the last 45 minutes are used for exercises in the class. Now we start with entropy. First, I want to talk about the discrete random variables, a brief definition. Consider x a discrete random variable, taking its value from the alphabet set chi. Then, the discrete random variable is characterized by the probability mass function, p of x, which equals the probability that x it is equal to x for every x from the chi set, such that sum of all x's from the domain of this course, p of x, it is equal to 1. This is also known as a normalization condition. For every x not in chi, p of x it is equal to 0. And for all the other x's in chi, p of x it is between 0 and 1, excluding 0. Consider the experiment of flipping a fair coin. Let x be defined as 1 if the result of flip it is head, and 0 if it is a tail. Then, since the result is a random process, x is a discrete random variable, and its value are from the set chi, which has the elements 0 and 1. And the probability mass function is as the following: p of x equals the probability of x equal to x, which has two possible values, either 1 over 2 for x equal to 1 or 1 over 2 for x equal to 0, since the coin is a fair coin. Otherwise, p of x it is equal to 0 for every x not in the set 0 and 1. Furthermore, we can check it. Sum of all x's from chi, p of x, equals p of 0 plus p of 1. Based on the equation 2, this sum it is equal to 1, which means the normalization condition is satisfied. So p of x can represent a probability mass function distribution according to x. Now we give a definition of the entropy. By definition, the entropy h of x of a discrete random variable x is given as h of x equal to minus sum of all x's p of x log with base 2 of p of x, where log with base 2 denotes the logarithm with base 2. P of x is the property mass function of discrete random variable x. In that case, the entropy is measured in units of bits. H of x, which is given by equation 3, is also known as Shannon entropy. Consider again the experiment of flipping a fair coin. Using the property mass function given by equation 2, which I am recalling it on this slide again, highlighted in red. We get the following for the entropy. H of x, it is equal to minus sum of all x's from the domain of this course, p of x log with base 2 of p of x, equal. Now chi has the values 0 and 1, so only two elements. Then the sum can be written as p of 0 log with base 2 of p of 0 plus p of 1 log with base 2 of p of 1. Since the p of 0 and p of 1 are both equal to 1 over 2, then we can replace it and we find out minus all the parentheses, all 1 over 2 log with base 2 of 1 over 2 plus 1 over 2 log with base 2 of 1 over 2. If we calculate this sum, we get 1 bit, where the log with base 2 of 1 over 2, which is equal to minus log with base 2 of 2, equals to minus 1. Consider an experiment of two possible outcomes, P for being successful and Q for being a failure. Let x be a discrete random variable taking either the value 1 for successful or 0 for failure. The question is to calculate h of x. Now here again, chi is a set with elements 0 and 1. And since p of x is a probability mass function, then we have p of 0 plus p of 1, it is equal to 1. We denote p of 1 equal to p, p of 0 equal to q, as given on the problem. Thus, you get q equal to 1 minus p. This is because p of 0 plus p of 1, it is equal to 1. Then the entropy of x is, we use the formula on the first line, h of x equal to minus sum of all x's from chi p of x log with base 2 of p of x. X takes two value, 0 or 1, then we replace this one. On the second line, you get equal to minus on the parenthesis p of 0 log with base 2 of p of 0 plus p of 1 log with base 2 of p of 1. We replace p of 0 with 1 minus p and p of 1 with p. Then you get minus 1 minus p all times log with base 2 of 1 minus p plus p log with base 2 of p. This indicates that the Shannon entropy h, it is a function of p, the last expression on this equation. If we plotted h of p as a function of p, we'll find the graph as it is shown on this figure, which is a bell-like shape. From this graph, we can notice this one, that at p equal to 0.5, which also q becomes 0.5, the entropy, it is maximum and it is equal to 1 bit. Here we have also assumed that x log with base 2 of x goes to 0 for x equal to 0. That is, x decreases faster to 0 than absolute value of log with base 2 of 0 increases to infinite. Next, we give the entropy with an arbitrary base b. By definition, the entropy h with base b of x with any arbitrary base b of a discrete random variable x is given as h with base b of x equal to minus sum of all x's from chi p of x log with base b of p of x, where log with base b denotes the logarithm with base b and p of x it is the property mass function of the discrete random variable x. In the case when b equal to the natural logarithm base e, the entropy is measured in units of knots. It is possible to transfer from an arbitrary base b to another base a. For that, consider the entropy definition in two different bases, namely a and b, for a discrete random variable x in chi. We write this as in equation 5 and 6. H of a of x, it is equal to minus sum of all x from chi p of x log with base a p of x. And h with base b of x, it is equal to minus sum of all x from chi p of x log with base b p of x. Next, we use a property of the logarithm. Logarithm with base a of p equals to the ratio of the logarithm with base b of p over logarithm with base b of a. If we replace this into the equation 5, then we get entropy with base a of x, it is equal to minus sum of all x p of x. Then you get log with base b of p of x over log with base b of a. You could notice that 1 over log with base b of a does not depend on x, so I can take it out of the sum. Then I arrive on the second line of the equation 7, minus 1 over log with base b of a, sum of all x's p of x, log with base b of p of x, which if I combine together the minus with the sum, we get entropy with base b of x. Then all is divided by log with base b of a, or can be written h with base b of x equal to log with base b of a times h with base b, a of x, and this is the equation 8. Now we can give some remarks on the entropy. So we give different measures of the entropy in the following. The first one, we see the entropy is a measure of uncertainty of x, a random variable. So entropy h of x of a discrete random variable x can be seen as a measure of the uncertainty of that random variable x. We can illustrate this one with an example. Consider again the experiment of two possible outcomes: successful with probability p and failure with probability q. X is the discrete random variable taking either the value 1 for successful or 0 for failure. The uncertainty on x depends on p, and the highest uncertainty on x occurs when p equal to q equal to 1 over 2, which corresponds to the maximum of entropy h, as shown in the previous exercise. Consider another experiment. For example, consider the experiment of opening a closed door. There are two possible outcomes of this. The door is open with probability p, and the door doesn't open with probability q. When you push or pull it, x is the discrete random variable taking either the value 1 for the door is open or 0 for the door doesn't open. The uncertainty on x depends on p, and the highest uncertainty on x occurs when p is equal to q equal to 1 over 2. That is, if you don't know whether to push or pull the door because the label push or pull is missing, the chances are 50 to 50%, which corresponds to the maximum of the entropy, h of x equal to 1 bit. Other measures from entropy h. Consider h of x in bits as the following, h of x equal to minus sum of all x's from chi p of x log with base 2 of p of x. This is by definition. If we combine the minus in front with log with base 2 of p of x inside the sum, then we can write sum of all x from chi p of x log with base 2 of 1 over p of x. Moreover, we can write this one as the expected value with probability distribution p of x of the function log with base 2 of this ratio p of 100% over p of x, where the expression for the expectation value of a function g of x of the discrete random variable x is used as the following: e p of g of x equals to sum of all x from chi g of x p of x, and p of 100% it is equal to 1, which gives the probability of a completely known discrete random variable x, or completely certain. EP denotes the expected value with probability distribution p of x. Therefore, remark 2, the entropy of the discrete random variable x with probability mass function p of x can be interpreted as the expected value of the random variable log with base 2 of the ratio p of 100% over p of x. That is, h equals the expected logarithm of the likelihood ratio. Now we can arrive to the remark 3. The expected value of logarithm of the likelihood ratio can be interpreted as a relative distance, which is an information theory measure of the measured probability of occurrence of x, p of x from the p of 100%, which corresponds to completely describe the discrete random variable x. That is, it is an information theory measure of uncertainty. The Venn diagram can be used to represent an entropy, Shannon entropy. This is in analogy with a Venn diagram of the sets. On the right hand side on the figure below, I've shown in a Venn diagram the set A with elements A, B, C. U, it is the universal set, and A, it is represented by a circle, a red circle here, where inside are listed the elements of the set A, B, and C. Similarly, also the entropy h of x of the x random discrete random variable could be represented by a single circle, where inside are listed all the elements of the alphabet set chi, like A, B, and C. Now we arrive at the remark 4. The entropy of the discrete random variable x with probability mass function p of x can be interpreted as the information required on average to completely describe the discrete random variable x from the alphabet set chi, or it is the average missing information on completely describing the discrete random variable x. We illustrate this one with this example. Consider again the experiment of opening the door. Let x be a discrete random variable such as x equal to 1. If the door opens successfully and x equal to 0, if the door fails to open, we choose to either push or pull it. The success of the outcome of this experiment depends on the information known a priori. That is, if we knew a priori that a push or a pull opens the door, then the uncertainty is lowest possible value, equivalent to h of x being equal to 0, because in that case p is equal to 1 and q is equal to 0. In contrast, the maximum h of x, and so the i's uncertainty, occurs for completely unknown to us whether we have to push or pull the door. Therefore, in the situation of complete missing information on whether to push or pull the door, the uncertainty of the experiment outcome is maximum. And so h of x it is equal to 1 bit, and p it is equal to q equal to 1/2. Remark number 5. More precisely, as it will be demonstrated next lecture, the entropy of the discrete random variable x with property mass function p of x can be interpreted as the average self-information contained in the discrete random variable x from the alphabet set chi, but it is not provided or described. That is, it is the average missing information on completely describing discrete random variable x. Consider the experiment of the decision made in the court of law. Let x be a discrete random variable such that x it is equal to 1 corresponds to the right decision and x equal to 0 to wrong decision. The success of the outcome of this experiment depends on the amount of evidence known a priori. That is, if a person has some evidence that could not clarify an unclear situation, which represents a self-information, but it is not provided to the court, which is a missing information, then this corresponds to highest uncertainty on making the right decision, and so the maximum h of x. Consider another example. Consider the experiment of success made in scientific discovery. Let x be a discrete random variable such that x equal to 1 corresponds to a discovery made and x equal to 0 to a discovery not made. The success of the outcome of this experiment may depend on the amount of literature available. That is, if the publishers reject often submitted manuscripts, which represent some self-information to the authors, but not provided to the others, and hence it is a missing information, then this corresponds to the highest uncertainty on achieving scientific discovery for others, and so the maximum h of x. Therefore, that might be used as a reason that increasing the number of accepted manuscripts leads to new scientific discoveries. Comparison with Boltzmann's entropy. Boltzmann's entropy S of a micro-canonical ensemble with total number of states omega is given as the following: S equal to kb ln of some omega, where kb it is the Boltzmann constant and ln is the log with base e. S is a measure in physics of the disorder in the system. Larger the number of states, more disorder, and larger the entropy S. To note, it is the following. Knowing that the probability of every state k is p of k equal to 1 over omega, that is a constant, then the sum of all k's of 1 over omega it is equal to 1. Therefore, S of equation 9 can also be written in the following form: minus kb sum over k's of 1 over omega ln of 1 over omega, which equals minus kb sum over k pk ln of pk. So the sum runs over all discrete states k. Note that both equation 3 given before and equation 10 given on this slide are equivalent up to the constant kb, and if log with base 2 it is replaced by log with base e ln, or vice versa. Other definitions of the Shannon entropy. Entropy h of x of a discrete random variable x can be seen as the average length of the shortest description of x, or the average number of binary questions that we can ask to completely describe x. For example, consider again the case of the random variable x, where x can take two values, either 1 or 0. 1 with probability p and 0 with probability 1 minus p. Determine the value of x with a minimum number of binary questions. An efficient question to ask is this one. Is x equal to 1? The answer can be either yes or no, with probability 1, because there are only two possible values of x. Whatever the answer is, there is no need for a second question. Therefore, the expected number of questions, it is n equal to 1, which equals the maximum value of the entropy 1 bit for this kind of probability mass distribution. And we have shown this on the previous slides. In general, we expect number of questions to be between h of x and h of x plus 1. The overhead of plus 1 is going to be explained on some other lectures on this course. For the moment, it is just an expectation. Consider another example. Consider a discrete random variable x which can take up to 4 values possible, a, b, c, d, each with the following probability: p of a 1 over 2, p of b 1 over 4, p of c 1 over 8, p of d 1 over 8. I have to determine first Shannon entropy h of x and the value of x with a minimum number of binary questions. First, let's calculate the Shannon entropy. Using the formula h of x equal to minus sum of all x from the domain of this course, p of x log with base 2 of p of x equals minus, then we write the sum as 1 over 2 log with base 2 of 1 over 2 plus 1 over 4 log with base 2 of 1 over 4 plus 1 over 8 log with base 2 of 1 over 8 plus 1 over 8 log with base 2 of 1 over 8. On the third line, I've used the properties of the logarithm. Logarithm of, in general, of log with base 2 of 1 over 2 to the power n, it is equal to minus log with base 2 of 2 to the power n, which is equal to minus n log with base 2 of 2. Log with base 2 of 2, it is equal to 1, then all this one, it is equal to minus n, which is for some integer n. So this is used on the third line. Then you get minus in front with a minus inside, minus n gives you plus, then you get 1 over 2 log with base 2 of 2 plus 1 over 4 log with base 2 of 2 to the power 2 plus 1 over 8 log with base 2 of 2 to the power 3 plus 1 over 8 log with base 2 of 2 to the power 3. Then using the formula in red, which I described, you get 1 over 2 plus 2 times 1 over 4 plus 3 times 1 over 8 plus 3 times 1 over 8. Then if we write this one, you get 1 over 2 plus, the second give 1 over 2 plus, the third 3 over 8 plus 3 over 8, the last one. Then if we sum this one, you get 7 over 4 or 1.75 bits. Now, let's determine the number of questions that we have to ask to completely describe the random variable x. An efficient question is this one: is x equal to a? And this is with probability 1, because we can always ask this question. First question can be always asked. The answer can be either yes or no. If the answer is no, then the second question is asked. However, the probability of asking the second question, it is with probability 1 over 2. because we'll ask this question only if the first answer is no, out of two possible answers, yes and no. Then this question is x equal to b? And the answer for this one can be either yes or no. If the answer is no, then the third question is asked with probability of 1 over 4, which is equal to 1 over 2 from the answer of the question 1, and 1 over 2 times 1 over 2 from the answer of question 2. And this question is x equal to c? The answer can be either yes or no. If the answer is no, then the fourth question is not needed to be asked. The value certainly is x equal to d. Therefore, the expected number of question is given as the following: n equal to sum of k from 1 to 3 of xk times p of k, where xk equals number of questions at each step k. But this one, at each step we asked a single question, so this means x of k is equal to 1. Then replacing xk equal to 1 for every k, then we have 1 times 1 plus 1 times 1 over 2 plus 1 times 1 over 4. Then if we calculate this one, it is equal to 7 over 4, or 1.75. Thus, it equals h of x, which is the minimum expected number of questions that we can ask. Now let's describe some properties of the entropy. The first lemma, it is this one: the Shannon entropy of a discrete random variable x is non-negative. That is, h of x it is greater or equal to 0. This can be proved easy from the definition, since p of x it is greater than 0 rigorously and less equal to 1 for every x from the domain of discourse chi. We have log with base 2 of p of x less equal to 0 by definition of the logarithm with some base 2. And if you multiply both sides by -1, then the sign of inequality changes direction. So minus log with base 2 of p of x, it is greater or equal to 0. Therefore, if we multiply this one by p of x, both sides, then the sign of equality does not change, because p of x it is between 0 and 1. Then we get minus p of x log with base 2 of p of x greater or equal to 0. Now, if we sum all these terms, sum of all non-negative terms must give me a sum which is non-negative. But that sum, it is the Shannon entropy. That proves that h of x it is greater or equal to 0. Now, let's give the definition of the joint entropy. So far, we consider one discrete random variable, x. Next, we are going to consider the definition when I have two discrete random variables. Let's say x and y. So let x and y be two discrete random variables with alphabet set chi and upsilon, respectively. The joint property mass function p of x and y is defined such that p of xy equals the probability that x take the value x and y take the value y. And moreover, the sum over all x's from chi and sum of all y's from upsilon, p of xy, it is equal to 1, which is the normalization condition that we called before. And p of xy it is equal to 0 for every x not in chi and for every y not in upsilon. And p of x and y it is greater than 0 rigorously and less equal to 1 for every x from chi and for every y from epsilon. Now we determine the marginal probability mass function. By definition, let x and y be two discrete random variables from the alphabet set chi and epsilon, respectively. The joint probability mass function is p of x and y. The marginal probability mass functions of x and y random variables, respectively, p x of x and py of y are defined as the following. Px of x, it is the sum over all y's from epsilon, p of xy. And p of y, it is the sum over all x's from chi of p of x and y. Now we can determine the so-called joint entropy. The joint entropy h, x and y of two discrete random variables x and y with a joint probability mass function p of xy, it is defined as the following. Similar to the one-dimensional case, p of xy, it is equal to minus sum of all x's from x, sum of all y's from the epsilon, p of xy log with base 2 of p of xy. It can be found the following. Similar to the one discrete random variable case, that joint entropy of x and y, which is equal to minus sum of over all x's from chi, sum of all y's from epsilon, p of xy log with base 2 of p of xy. We group together minus with log with base 2, and we write the double sum as p of xy log with base 2 of 1 over p of xy. And this one can be seen as the expected value with probability distribution, the joint probability mass function p of xy of this function log with base 2 of this ratio of the probabilities p of 100% over the p of the joint probability mass function p of xy. We can also represent this graphically using the so-called Venn diagram. So on blue I've given h of x, in red h of y, both Shannon entropies for single discrete random variables. Then the joint Shannon entropy of the two discrete random variables x and y, it is the union of these two circles. Next definition is the so-called conditional entropy, h of y given x. The conditional entropy h of y given x for two discrete random variables x and y with joint probability mass function p of xy is defined as h of y given x, it is equal to sum of all x's from chi p of x, h of y given x equal to x, where h of y given x equal to x equal minus sum of all y's from epsilon p of y given x log with base 2 of p of y given x, and conditional probability p of y given x is the conditional probability given such p of y given x equals to p of x and y over p of x. We can also find out similarly that h of y given x, which is given by substituting into the equation 14 the second line, then you get p of x given x, sum of all in front, sum of all x from chi with minus in front, sum of all y's from epsilon, p of y given x log with base 2 of p of y given x. Now on the second line I've used the definition above of the conditional property. from P of y given x equal to P of x over P of x and y over P of x given x, I have written the joint property mass function P of x and y as P of y given x times P of x, the marginal one. Then we have sum of minus sum of all x from chi, sum of all y's from epsilon, P of x and y log with base 2 of P of y given x. Now this can be seen as the expected value with property mass function, the joint property mass function P of x and y of this function log with base 2 of this ratio of probabilities P of 100% over P of y given x. Venn diagram of the conditional entropy, it is shown in the following. With blue, I've shown the h of x. In red, it is shown h of y. Then h of y given x, it is shown on orange. So all the area of h of y which does not overlap with h of x, it is h of y given x. So as a remark, conditional entropy of a discrete random variable y given the discrete random variable x can also be defined as the expected value of the entropies h of y given x equal to x of the conditional probabilities P of y given x averaged with probability P of x given x of the conditional discrete random variable x. Now can use a chain rule. The joint entropy h of x and y of two discrete random variables x and y and conditional entropy h of y given x are related as the following. Joint entropy of x and y is equal to h of x plus h of y given x. A simple proof can be shown using the Venn diagram in the following. Now we can notice on this Venn diagram the blue gives the h of x, the red gives h of y. Then h of y given x, it is all part of h of y which does not overlap with h of x. Right? Now you could notice that if you sum up to that one, h of y given x, the all h of x, then you will get the joint Shannon entropy h of x and y. Alright, so this is a simple proof. However, we can use a long proof of this one using the so-called relationship of the probabilities. So log with base 2 of P of y given x, it is equal to log with base 2 of P of x and y over marginal P of x of x. Right? Now this last, the right hand side of the first expression, could be further written based on the properties of the logarithm as the log with base 2 of P of x and y minus log with base 2 of marginal P of x. It can be found that h of y given x, which is given minus sum of all x's from chi P of x and sum of all y's from epsilon P of y given x log with base 2 of P of y given x to be equal to minus sum of all x's, sum of all y's, P of xy. Then you can write log as a difference of two logs, log with base 2 of P of xy minus log with base 2 of P of x. Now I can write this into two sums. The first sum, it is minus sum over all x's, sum over all y's, P of xy log with base 2 of P of xy, minus the second sum minus on the parenthesis minus sum of all x's, sum of all y's, P of xy log with base 2 of P of x. Now on the second sum, as highlighted in red, if we calculate the sum of all y's from epsilon P of xy this will give the marginal with respect to x. Then the first sum gives me the third line gives me the joint entropy of x and y. Then the second sum can be written minus on the parenthesis minus. Then, as I said, the sum of all y's from epsilon of p of xy gives me the marginal with respect to x. Then I can simplify this one, write simply p of x, log with base 2 of p of x. Now on the last line, the term on the parenthesis determines Shannon entropy of x random variable, h of x. Then I obtain difference between the joint Shannon entropy of x and y minus the entropy of x. Or the last expression could be reformulated, rearranged on this form: h of x and y, it is equal to h of x plus h of y given x. Similarly, we can also determine the conditional entropy of the other variable x on y. So the conditional entropy h of x given y for two discrete random variables x and y with joint property mass function p of xy, it is defined similarly. H of x given y, it is the sum now of over all y's from epsilon, p of y, h of x given y equal to y, where now the entropy of x given y equal to y, it is equal to minus sum of all x's from chi p of x given y log with base 2 of p of x given y. And p of x given y is the condition probability, which is simply given as the ratio of the joint property mass function over the marginal with respect to y. Similarly, it can be found that h of x given y, which is given by definition as minus sum of all y's from epsilon, p of y, and sum of all x's from chi p of x given y log with base 2 of p of x given y, to be equal to minus sum over all x's, sum over all y's, p of x and y log with base 2 of p of x given y, or as the expected value with probability mass function p of x and y of this function log with base 2 of the ratio of the probabilities p of 100% over p of x given y. The same chain rule applies also here. The joint entropy h of xy of two discrete random variables x and y and conditional entropy h of x given y are related as the following: h of x and y, it is equal to h of y plus h of x given y. Now the proof, a simple proof, follows as previously using the Venn diagram. So on blue we can write the h of x, on red h of y. Now I look at h of x given y. Then this is that part of the blue circle which represent the whole circle h of x, which is as no parts from h of y. Now if you add to this one the whole circle red, which is h of y, then of course you will get the joint entropy between x and y. And this is a proof of the equation 17. However, we are going to follow the same guidelines as before, only slightly different, just to make it a different proof. But actually, essentially it is quite similar to the previous proof. Now we use this relationship between the property mass functions and the marginals and the conditional probabilities. Log with base 2 of p of x and y, it is equal to log with base 2 of p of x given y times the marginal p of y of y. Now the logarithm with base 2 of the product, it is the sum of logarithms log with base 2 of p of x given y plus log with base 2 of marginal p of y of y. Now we start with joint Shannon entropy of x and y, h of x and y, and this is the normal definition of Shannon entropy, of joint Shannon entropy, minus sum of all x's from chi, sum of all y's from epsilon, p of x and y log with base 2 of p of x and y, equal minus sum of all x's from x from domain of discourse of x, sum of all y's from the domain of discourse of y, epsilon, p of x and y, and we write log with base 2 of p of x and y using the first equation, as a sum of two logarithms with base 2, as shown on the second line. Now on the third line, I've written the single double sum into two terms, which are double sums. The first, it is the minus sum over all x's from chi, sum over all y's from epsilon, p of x and y log with base 2 of p of x given y. And the second sum, it is minus sum of all x's from chi, sum of all y's from epsilon, p of x y log with base 2 of p of y of y. Now on the second term, on the third line, the terms in red, sum of all x's from chi and p of x and y, if we perform this sum, this will give me the marginal with respect to y random variable, as it is shown on the fourth line. The first term on the third line gives me the conditional entropy of x given y, and minus sum of all y's from epsilon, p of y log with base 2 of p of y. And the second sum gives me the Shannon entropy of the random variable y. Then I get h of x given y plus h of y, what I wanted to prove. As a remark, in general, h of x given y, it is different from h of y given x. And this can be illustrated on the figure below with Venn diagrams. Alright, so we have shown on this, on the left hand side, how the h of y given x looks. Then on the right hand side of the Venn diagram, I have shown h of x given y. Now you could notice that these two parts may not necessarily be equal. All right. Now, however, using the chain rule, we can also have this one, h of x and y, which is equal to h of x given y plus h of y, h of x and y equal to h of y given x plus h of x. Now from these two equations we get that h of x given y plus h of y, it is equal to h of y given x plus h of x. Therefore h of x minus h of x given y, it is equal to h of y minus h of y given x. All right. These two terms are indeed equal. Now we can give a corollary. Let x and y and z be three discrete random variables. Then h of x and y given z, so this is the conditional entropy of x and y given z, it is equal to conditional entropy of h x given z plus the conditional entropy of y given x and z. The proof, it is on the next slide. First, we show a easy proof using the so-called Venn diagram. All right. Now, on this Venn diagram, I have plotted h of x, h of y, h of z. H of x is in blue, h of y in a red circle, and h of z in green circle. Right? Now, on each, I have indicated these terms. First, h of x and y, which is the joining of a red circle and the blue circle. Right? Now, h of x given z, Now h of x given z, if I show on here, will be this part on here. All right, so h of x here, all right, excluding the part with z, then it is all this part that it is shown on here. Now if we show h of x and y given z, all right, then this will be all this part that it is shown on here, all right, on the gray scale. All right. H of y given x and z, it is all this part which is shown surrounded by this by the yellow thing. All right. Now you could notice now from this one that h of x and y given z, right, which is this one, equals two parts. It is composed of two parts. First, h of x given z, right, plus h of y given x and z. Because if I would show this h of x and y given z, it is all this part on here. All right, h of x given z, it is what it is on orange here. And h of y given x and z, it is what it is on yellow. And the sum of the orange surrounded part plus the yellow surrounded part gives me the whole h of x and y given z. So this is a simple proof by Venn diagram. However, we can also follow a proof, analytical proof. H of x and y given z, it is equal to the sum of all z from z, p of z, h of x and y given z equal to z. That's based on definition. Now this is equal to, now I replace h of x and y given z equal to z as minus sum of all x's from chi, sum of all y's from epsilon, p of x and y given z log with base 2 of p of x and y given z. Then on the third line, I've written minus sum of all z from z, p of z, double sum of over all x's over all y's. Then I have p of x and y given z as on the second line, then log with base 2. Then on here, p of x and y given z has been written as product of two terms, p of x given z times p of y given x and z. Right? Now log with base 2 to jump on the fourth line of this product is written as a sum of logs of two terms, log with base 2 of p of x given z plus log with base 2 of p of y given x and z. Then we obtain two sums, one on the fourth line and the next sum on the fifth line. Now on the fourth line, I've joined together terms in red, p of z given z, which can be put inside the sum over y because does not depend on y. However, p of z given z times p of x and y given z can give on here, if I sum over all y's, can give me p of x and z. So the joint property mass function between x and z. Then I obtain minus sum of all x's which are left from chi, sum of all z from z, p of x and z log with base 2 of p of x given z. Now on the fifth line, I join together the terms in blue, p of x z given z times p of x and y given z. This will give me p of y given x and z. Then the triple sum remains as it is, and the log with base 2 of p of y given x and z. Then if I look on the sixth line, the first sum gives me the entropy of x given z, plus the second term, triple sum, gives me the entropy of y given x and z. And this is what I wanted to prove. Now here it is shown a case, an exercise, how to calculate the joint, to calculate several entropies if I know the joint probability mass function between two random variables x and y, right? And this is given by this table, and I want to calculate h of x, h of y, h of x and y, h of x and given y, h of y given x. Then we can simply calculate h of x, then you get 7 over 4 bits. Then we can calculate h of y, then we get 2 bits from this. Then we can calculate the joint entropy of x and y, then you get 27 over 8 bits. Here I've used that 0 times log with base 2 of 0 it is equal to 0, and log with base 2 of 1 over 2 to the power k, as we demonstrated also before, it is equal to minus k. Then we can calculate also the marginal, the conditional entropy, h of x given y and h of y given x on here. For this one I've used these two formulas, h of x and y, it is equal to h of x plus h of y given x, and h of x and y, it is h of y plus h of x given y. Then you could calculate h of y given x as h of x and y minus h of x, and you get 13 over 8 bits, and h of x given y as h of x and y minus h of y, and you get 11 over 8 bits, and you can see that they are different. All right. Moreover, h of x minus h of x given y, it is 3 over 8 bits, and h of y minus h of y given x, it is 3 over 8 bits, so they are equal. All right. That it is discussed in details next lecture, but we can give a simple demonstration on this slide. So if we calculate h of x minus h of x given y, then this will give me the intersection between the two circles, h of x and h of y. So also h of y minus h of y given x will give me the intersection between the two circles. But this is the same for both. So this means that these two terms are equal. In summary, what you should remember from this lecture, you should understand the course structure and evaluation. You should understand a discrete random variable and its property mass function. You should be able to calculate the Shannon entropy h of x of a discrete random variable x knowing its property mass function. You should understand the properties of h of x. You should also be able to calculate the joint Shannon entropy h of x y of two discrete random variables, let's say x and y, if you know the joint property mass function. You should be able to calculate the marginal property mass functions, knowing the joint property mass function of two discrete random variables x and y. You should be able to calculate the conditional entropy h of x given y or h of y given x of two discrete random variables x and y, knowing the joint property mass function. And this is all for today. Thank you very much for your attention. See you next time.